Dear students, today we will discuss the theorems of the chapter circles from class 9 mathematics. First theorem 9.1, equal chords of a circle subtend equal angles at the center. Students, before discussion of this theorem, we should know what is the circle. Here is one picture. Circle is the collection of all points on a plane which are at equidistant from a fixed point is called circle. The fixed point is called here the center. This is the center. And the fixed distance in the second picture is the radius. Students, next we will discuss what is chord. Line segment joining any two points on a circle is called chord. You see the diagram here. AB and CD are the chords of the circle. OA, OB, OC and OD are the radii of the circle, and O is the center of the circle. Now we will discuss what it is given in the theorem. In the theorem it is given AB and CD are two equal chords of a circle with center O. Now angle AOB and angle COD are the angles subtended by chords AB and CD respectively at center O. So what to prove now? Angle AOB equal to angle COD. Now you come to the proof part of the theorem. In between triangle AOB and triangle COD, OA equal to OC, radii of same circle. Again OB equal to OD, radii of same circle, and it is given AB equal to CD. So students, triangle AOB congruent to triangle COD using SSS congruence criterion. As corresponding parts of congruent triangles are equal, angle AOB equal to angle COD. Why? Because corresponding parts of congruent triangles are equal, and hence it is proved. Next, theorem 9.2. If the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Students, what is given there? Angle AOB and angle COD are two angles of equal measure subtended by the chords AB and CD respectively at the center of the circle. You observe the diagram. According to the theorem, it is given AOB equal to angle COD. Come to the proof part. Before that, we should know what to prove. Length of chord AB equal to length of chord CD, that is AB equal to CD. In between triangle AOB and triangle COD, OA equal to OC. Why? Radii of same circle. And it is given angle AOB equal to angle COD and OB equal to OD, radii of same circle. So students, triangle AOB congruent to triangle COD using SAS congruence criterion. As corresponding parts of congruent triangles are equal, So, AB equal to CD, that is CPCT corresponding parts of congruent triangles are equal. So, students, this is theorem 9.2. Now, we will proceed to theorem 9.3. What is the statement? The perpendicular from the center of a circle to a chord bisects the chord. Students, what is given? OM is the perpendicular from the center O to the chord AB of the circle. What to prove? AM equal to BM. Now, what is the construction we have made here? Join OA and OB. Come to the proof part. In between triangle AMO and triangle BMO, AMO angle is equal to angle BMO. Why? It is 90 degree. Both the angles are 90 degrees. And OA equal to OB, radii of the same circle, and OM equal to OM, which is common to both the triangles. Therefore, triangle AMO congruent to triangle BMO using RHS congruence criterion. So, as we know, corresponding parts of congruent triangles are equal. So, AM equal to BM. Why? Because corresponding parts of congruent triangles are equal. So, students, this is theorem 9.3. Next, we will proceed to theorem 9.4. What is the statement? The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. So, students, you see the diagram. What it is given? Line OM is drawn through center O to the midpoint of chord AB. So, what to prove? We have to prove OM is perpendicular to the chord AB. Now, what to do the construction? Join OA and OB. Clear? Next, come to the proof part. In between triangle AMO and triangle BMO, AM equal to BM, because students, it is given AM is the midpoint of AB. So, AM equal to BM. Again, OA equal to OB. Why? Radii of same circle, and OM equal to OM, which is common to both the triangles. Therefore, triangle AMO congruent to triangle BMO using SSS congruence criterion. As corresponding parts of congruent triangles are equal, so angle AMO equal to angle BMO, corresponding parts of congruent triangles. But you observe the diagram, you will find angle AMO and triangle BMO, the sum is 180 degree. Why, students? Because they are linear pair of angles. So, their sum is 180 degree. What we know, students? Angle AMO equal to BMO, proved earlier, and their sum is 180 degree. So, measure of each angle AMO equal to BMO, that is 180 degree by 2, that is 90 degree. So, now if angle AMO and BMO are both 90 degrees, so what is your conclusion now, the line OM is perpendicular to AB. So, this is theorem 9.4. You come to theorem 9.5. Students, here, what is the statement? Equal chords of a circle, I underlined, are equidistant from the center, or equal chords of congruent circles are equidistant from their respective centers. That means, students, here you can take the same circle or you can take two distinct circles. So, students, here you must know, before proof of the theorem, what is the meaning of congruent circles. Two circles are said to be congruent if they have the same radii. Now, you observe both the circles. I have taken two congruent circles. You observe one circle is passing through the center of the other one, and the other circle is also passing through the center of the first one. It means both are congruent circles. Distance from the center to the circle is the radius. So, these two circles are congruent circles because both have same radii. Clear? Now, we will proceed to the next. Students, you must know what is the distance. It is the shortest length between 2 points. If you are taking 2 points on a plane, the shortest length is the distance between the 2 points, or length of line segment connecting the 2 points. But the distance of a line or line segment from a point is the perpendicular distance from the point to the line or the line segment. Here, students, we have taken one point A and BC is one line segment, and this distance between BC and the point A is this line segment, vertical line segment, which is the distance between a point and the line segment. Next, come to the theorem now. What it is given? You observe the diagram. Here it is given PQ and RS are two equal chords of a circle with center O. What to prove? PQ and RS are equidistant from the center O. Come to the construction part, students. Draw OL perpendicular to PQ and draw OM perpendicular to RS and join OQ and OS. Now, here, students, you are getting two triangles. One is OLQ, another is OMS. Come to the proof part. What is given, students? PQ equal to RS. According to the construction, OL perpendicular to PQ and OM perpendicular to RS. But we know that perpendicular from the center of a circle to a chord bisects the chord. Clear? We know perpendicular from the center of a circle to a chord bisects the chord. So, what is the length LQ now? LQ equal to half of PQ. Similarly, MS equal to half of RS. What we know? PQ equal to RS. It is given. If PQ equal to RS, half of PQ equal to half of RS. But what is the value of half of PQ? That is LQ. What is the value of half of RS? That is MS. So, students, LQ equal to MS. Now, you observe both the triangles OLQ and triangle OMS. Angle OLQ equal to angle OMS. Both the angles are of measure 90 degree because these are the perpendiculars. OL perpendicular to PQ and OM is perpendicular to RS. So, OLQ equal to OMS, both 90 degrees. Again, OQ equal to OS, radii of same circle, and LQ equal to MS, just you have proved. Now, what is your conclusion? OLQ triangle congruent to triangle OMS using RHS congruence criterion. As corresponding parts of congruent triangles are equal, so OL equal to OM. CPCT, you know corresponding parts of congruent triangles. Clear? Next, as OL is the perpendicular distance from center O to PQ and OM is the perpendicular distance from center O to RS with OL equal to OM. What it implies? PQ and RS are equidistant from the center O. I hope the theorem is clear to you. Now, students, we will proceed to the next theorem, that is Theorem 9.6. What is Theorem 9.6? Chords equidistant from the center of a circle are equal in length. Students, you observe the diagram. If you observe the diagram and you will read the statement of Theorem 9.6, what it is given? It is given PQ and RS. Observe carefully, PQ and RS are two chords equidistant from the center O of the circle. What to prove then? PQ equal to RS. So, what to do? Under construction, draw OL perpendicular to PQ and OM perpendicular to RS. Finally, join OQ and OS. Clear? Now, come to the proof part of the theorem. Students, you observe both the triangles, triangle OLQ and triangle OMS. In between triangle OLQ and triangle OMS, OLQ equal to OMS equal to 90 degree according to the construction, and OQ equal to OS, radii of a circle, and OL equal to OM given. So, what is your conclusion from the above proof? Triangle OLQ congruent to triangle OMS using RHS congruence criterion. Clear? As corresponding parts of congruent triangles are equal, so LQ equal to MS, corresponding part of congruent triangles. CPCT. Students, 2 times of LQ equal to 2 times of MS. I have written here. Why? 2 times of LQ equal to 2 times of MS. Because we have proved here LQ equal to MS. If LQ equal to MS, 2 times of LQ equal to 2 times of MS. But what is the value of 2 times of LQ? That is PQ. And what is the value of 2 times of ms? That is rs. Just we have discussed that as perpendicular from the center of the circle to a chord bisects the chord, so LQ equal to PL and MS equal to RM. So double of LQ equal to PQ and double of MS equal to RS. So students, I hope you understood the theorem. Now we will discuss theorem 9.7. What is the statement? The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Students, first you must know what is arc. All of you observe this circle. Arc is part of a circle. You see, I have taken 2 points on the circle, marked point A and point B. So now the complete circle I have divided into 2 parts. One part shaded red, another one part shaded black. So the red shaded portion is the minor arc and the black shaded one is the major arc. So students, you must know the definition of minor arc. If length of an arc is less than the semi-perimeter, then it is called minor arc. Students, I hope you know what is semi-perimeter. It is half of perimeter, and you know perimeter of a circle is the length of the boundary, and the formula to find perimeter of a circle is 2 pi r. What is 2? It is a constant. What is pi? It is the ratio between the circumference of a circle to the diameter, and r is the radius of the circle. So students, if 2 pi r is the perimeter, so semi-perimeter means half of it. And if the length of the arc is less than semi-perimeter, then it is called minor arc. So AB shaded red is the minor arc. Now we will discuss what is a major arc. If length of an arc is more than semi-perimeter, then it is called major arc. Now you observe the diagram. The black shaded part of the circle is the major arc. Let us consider the minor arc AB shaded red. Any point on the remaining part of the circle means any point on the major arc AB, that is shaded black. Now students, you come to the theorem. What it is given? Given an arc PQ. But students, I have taken here 3 diagrams. Figure 1, figure 2, figure 3. You observe carefully. An arc PQ of a circle subtending angle POQ at the center O and angle PAQ at any point A on the remaining part of the circle. Once more, you listen carefully and try to point out an arc PQ of circle subtending angle POQ at the center O and PAQ at any point A on the remaining part of the circle. So what to prove? Angle POQ is twice of angle PAQ. This is the objective of the theorem. You come to the proof part. Students, I told earlier, we have to prove this theorem by taking 3 different types of figures. Consider the 3 different cases as given in figures. In figure 1, arc PQ, observe carefully, which is minor. In figure 2, arc PQ is a semicircle, and in figure 3, arc PQ is a major arc. So, three different arcs we have taken, one is minor, one is major, another one semicircle. Now, what to do in order to prove? Draw ray AB passing through O. In all the cases, you will find angle BOQ equal to angle OAQ plus angle AQO, as an exterior angle of a triangle is equal to the sum of the two interior opposite angles. Again, in triangle OAQ, OA equal to OQ, radii of a circle, and OQA equal to OAQ, angles opposite to equal sides are equal. Now, you see angle BOQ equal to angle OAQ plus AQO, equal to OAQ is OAQ plus next OAQ is the value of OQA or AQO. So, students, what is the final? We got here BOQ equal to 2 times of angle OAQ. Similarly, we can prove angle BOP equal to 2 times of OAP. Adding 1 and 2, we get BOP plus BOQ equal to 2 times of OAP plus OAQ. It implies POQ equal to 2 times of PAQ. For the figure 3, where PQ is the major arc, angle POQ is replaced by reflex angle POQ, which is equal to 2 times of PAQ. And the remaining theorems of this chapter we will discuss in another one class. Thank you for your patience hearing.